If you've seen our earlier version of the talk, don't worry, I've varied it a bit and there's something new as well. So let's get started. So the background point of view is that, or the big picture question that sort of fundamentally this ties into is trying to figure out what exactly makes quantum computers tick. And sure, we have all these fancy quantum algorithms for various problems, but they seem to, we don't have a big stock of them at the end of the day, and we don't have a very systematic understanding of where to go and look for them. But somehow the idea is that there's something, maybe we'd benefit from having a systematic understanding of what exactly gives the benefit, and probably it has to do with something in quantum mechanics that's definitely different from known classical features. And now there's many candidates for this, but the one we're focusing on now is non-locality, or more generally, contextuality of it. So let's explain what contextuality is. So the point is that in quantum mechanics, theory doesn't let you do all possible measurements on a system at once. Only certain sets of measurements can be jointly performed. And now contextuality, you could think of it as sort of in terms of this picture. So if you just look at think of each of these as being some kind of joint observation, then each of them gives you a picture that kind of makes sense. So it looks like everything looks locally consistent, but then when you try to glue it together, it kind of doesn't make sense anymore. So let's make this a bit more precise next. So we work in a theory-independent setting. So we just started by saying that, okay, we have some finite set of measurements, and now there's a simplicial complex structure on those measurements, which just tells us which measurements are jointly possible. And it being a simplicial complex just says that it's downwards closed. So basically, if a set of measurements is jointly possible, then any subset of them is jointly performable as well. And now you might ask, okay, where does this simplicial complex structure come from? And we sort of take it as a given. But you can think that, okay, maybe it's something that the theorist told you that, okay, this is what our theory predicts. Or maybe the experimentalist says, oh yeah, these are the things we can do together. We're not unable to perform these other ones. I should also note that, then any measurement you get some outcomes, and for now we work in a setup where each measurement comes with a finite set of outcomes. This approach can be and has been extended to having general measurable spaces there as your outcome sets. But it's unclear if any truly novel phenomena arise there, so I'll just focus on the finite case. And now, once you have this set of measurements in place, that's your measurement scenario. And then you'd have some system, and you do some repeated measurements on it, and you'd get data out. So basically, you'd expect to see a joint probability distribution for any joint measurement. And now the only condition that we expect to hold here generalizes this idea of no signaling. So roughly you'd expect some joint measurement to behave the same no matter what other things you're measuring with it. In the situation where you actually, the situation that's described here, you might think of Alice and Bob, who are space-like separated, and both have two choices of a measurement. And in that case, this generalized no signaling condition just says that the choice of Alice's measurement doesn't affect the probabilities of Bob's measurements, and vice versa. So in effect, it's saying that Alice can't signal any information to Bob by making a choice of what measurement to make. So here's an example of this where we have now 4 measurements, so one for Alice and one for Bob. And each measurement gives you just binary outcomes. And then the possible joint measurements, or the maximal joint measurements, are just given by choosing one measurement at each site. And now you might imagine seeing probabilities like this. And this is actually one of those things that will be contextual as defined later. So this is the so-called PR box, which actually isn't feasible to build in quantum mechanics, but it's still quite interesting mathematically and sort of in the study of this kind of things. So now to get to the point of what contextuality is, you might say, okay, I don't like this thing. I want to be able to measure everything at once. Like maybe the theory that predicts that there's some limits on this is wrong, or maybe the experimentalists aren't quite good enough. There should be a way of measuring everything at once and getting reasonable answers. Well, if that were to be the case, then you'd expect that there should be a joint, doing then joint measurements on everything at once should give you a joint probability distribution on all the measurements at once. And moreover, this should explain the marginals that we actually observe. And now it turns out that sort of probability distributions on a set don't form a sheaf. So you might have this situation where everything sort of locally looks nice, but it doesn't glue together. So this joint probability distribution just might not exist at all. And in that case, you'd call the system contextual. So in other words, you have sort of these marginal distributions that when on their overlaps, they agree, but there's no way of gluing them together to get a single probability distribution that explains all of it. And now it turns out that nature is such, at least if you believe in quantum mechanics, and indeed this has also been demonstrated in multiple experiments. So in a slogan, you might then say that unperformed measurements don't have results, because you can't imagine a probability distribution that would explain the marginals we see that would also give you reasonable probabilities on everything. And now, if you're sort of a physics person or especially a foundation of quantum mechanics person, you might then start wondering, what does this say about nature and what does it say about the kind of theories we should believe? But here in this talk and this work, we're instead wearing our CS hats. So we're kind of asking, like, sure, but what can you do with this? What does contextuality give you? And there's already some hints that maybe it's related to the quantum speedup. So for example, in measurement-based quantum computation, you can do a situation where you have a very limited measurement-based quantum computer that can only do mod 2 linear things, and then giving it access to a contextual resource will let it do more things. And similarly, there's this work that roughly says that if you take a work in stabilizer quantum mechanics, well, that's classically simulable in polynomial time. But if you give it access to a single contextual state, or sorry, if you give it access to a so-called magic state, then you can promote it to universal quantum computing. And this result states that for odd dimensional computing, it's necessary for the resource to be contextual for it to be magic. And now there's some issues with generalizing this to qubit case, but there's hope that maybe something like that is true there as well. And a final example of this kind of situation is this fairly recent work that caused a lot of excitement. So Bravi, Gosset, and Koenig managed to show that there's an unconditional separation between quantum computers and classical computers in a somewhat limited setting. So this doesn't solve the big questions in complexity theory, but the interesting thing is that they don't need any complexity theoretic assumptions to prove this. And at the heart of this, even though, I mean, they weren't, so maybe these other guys were in the business of showing that, okay, contextuality, our favorite topic, is the reason, but these guys just wanted to prove an unconditional separation between quantum and classical. And it turns out that if you analyze it very carefully, there's a contextuality argument somewhere at the heart of this matter. And Sievert, who's a student here, is, I guess, at the moment busy writing up his analysis of this situation. So maybe we should analyze this contextuality as a resource. So if you want to think of this contextuality as a resource, you'd want to have systematic ways of comparing different contextual resources to each other and figure out when they're the same and when are they different. And there's already people have done things like this. So for example, the PR box I already mentioned has been studied in this context. And it turns out that if you have any two-party setup, no matter how many measurement settings you have, as long as all the outcome sets are binary, if you have enough PR boxes, you can get everything. But they also show that PR boxes don't generate absolutely everything. So if you have, there's an explicit tripartite quantum realizable box that you can't get, no matter how many PR boxes you have. So now there's two kinds of flavors or approaches to resource theories. So one would be to say, oh yeah, we have sort of an algebraic set of free operations, and then you can just ask whether you can start from some resource and apply these free operations to it to get another one. And alternatively, sort of in more CS point of view, you'd instead ask whether you can reduce the behavior of a system to another one in terms of some kind of a simulation. And in a sense, our current work is sort of generalizing and unifying ideas that are present in both of these approaches. Another way of thinking about what we're doing is that, well, we already have these empirical models, and there's these questions of, okay, how contextual it is. And now the question is, what are the morphisms? And you could answer it in two ways. So one is the sort of resource theory point of view. So if you can get E from D using these free operations, then there's a morphism, or that should be a morphism. And another way of thinking about this is in terms of these simulations. And a big part of our paper is setting both of these up and proving that they actually give you the same notion of convertibility. But today, instead, I'll just focus on this latter piece to have more time. So now if you have two of these boxes, what does it mean to have a simulation between them? Well, roughly, we just need to have a recipe. Or, I mean, first we start with a very limited notion of a simulation. I'll extend this later to a more powerful one. But as a first approximation, you might think like this. So you first have some recipe that says, oh yeah, if you need to pretend you have a box B, but instead you have a box A, what you do is that whenever you need to measure something in B, you give a recipe of what you need to measure in A. And then when you get some outcomes, you have another recipe that tells you what outputs to interpret in B as you having obtained. And moreover, it's not enough to have this data. You should get exactly the statistics of B out of this kind of simulation. And already this captures many things, so you can easily write down what does it mean for two empirical models to be isomorphic. But you can also restrict to focus on a submodel of some empirical model, or you can coarse grain your outcomes, so apply some function and even enlarge the outcome sets. And there's this funny contravariance business, so the inputs and outputs go in different directions. I won't say much about it now, but it's sort of similar situations happen somewhat often in mathematics where you have some kind of a space and something like a sheaf on it. And then how you'd relate to would be by having a map between the spaces and then some kind of a map between the sheaves in the opposite direction. So it's not that weird, but sometimes it can cause confusion when one part goes in a different direction than the other half. So more formally, we have these simplicial complexes that give you the measurement scenarios. So you'd want a map between those. And then moreover, you need a map of the outcome sets. And now the point of this being a simplicial map just says that, oh yeah, if you have a possible measurement in the thing you're trying to simulate, then it's the thing that simulates it, or its image, should always be a possible joint measurement as well. And now you can then calculate and show that actually if you have a morphism of these scenarios, any statistics or any empirical model you have here will then induce statistics on the other side. And it's sort of the obvious thing. You just see what kind of outcomes you observe with what probabilities if you see the original thing. And now you can define the category of interest, where now our objects are actually not just these measurement scenarios, but these empirical models. And then a morphism between two empirical models is a map between the measurement scenarios that takes the statistics of E to the statistics of E prime. And now we want to go a bit further, and the way we do it is to say, well, first of all, you might want to have stochastic things there. So you might want to say, oh yeah, you don't want to be deterministic. You might want to first randomize what to measure at the other place. And you might want to be able to then randomize what you do to the outcomes using classical randomness. But the other thing you might want to do is to say, oh yeah, don't just go and measure. If you need to simulate measuring x here, don't just measure a single thing on the other side. Measure a whole bunch of them. In fact, you might even give a whole recipe of saying, oh yeah, first measure this. Then when you get an outcome, here's a recipe what measurement to do next. And then based on that, you choose what to do next. And eventually get a whole string of measurements. And then that's what you use to interpret this. And the interesting thing is that this is already something that people have done in related things, although for somewhat different purposes. So for example, in measurement-based quantum computing, it's very essential that you can use earlier measurement outcomes to choose what further measurements to do. And this thing turns out to be a comonad on this category of these empirical models. And basically the plan is then to move to the co-classic category of this. So if we first had these fairly limited simulations, then the idea is that you can think of improving the power of A, but in a purely classical fashion. So you just sort of box A and think of all the measurement protocols you could run there as measurements on their own right, and just say that, okay, our simulation from A to B is now actually a map from MP of A to B. But you might want to go even further. So to allow for classical randomness, what you do is you'd say that you can use freely a classical resource, or something, a non-contextual box, to help you in making random choices. So anytime you need to make a random choice, you can just measure the non-contextual thing and use the randomness therein to get your outcomes, or I mean, help with your choices. Yeah, and then let's say a bit more. How does this go more formally? So we present this a bit differently in the paper, but it's sort of easier to define, or at least say, or give a hunch what it is in terms of recursive definition. So you can think of these measurement protocols as certain trees. So then the base case is just to say, okay, there's an empty measurement protocol which measures nothing. And then the other case is that you measure something in X, and then you have a function which tells you what measurement protocol to do next. And the function depends on, I mean, the input is the outcome of the measurement X you did. And now the outcome shouldn't be just any measurement protocol in the measurement scenario. It should be something that is still compatible with X, which means we look at the link of X if you're familiar with that. And now you'd want to actually, so this just defines what the measurements are of this new scenario. You should then tell what the outcomes are. Well, if you do a measurement protocol and finish, well, then you've just obtained an outcome for each of the measurements in it, and you just return that, and that's your outcome. And now you should be able to say when some measurement protocols are compatible with each other to get the simplicial complex structure. And then, I mean, the rough intuition, I'm not going to give the precise one here, is that if you can sort of run them along each other in parallel without ending up in trouble. So without ending up having to do incompatible measurements. Yeah, I'll just keep that part. So now it turns out that this operation indeed gives a comonad, and this is in fact a comonoidal one. So it means that it works well with the tensor product. And the rough intuition is that, well, if you think about this thing, for example, the co-multiplication, the point is that if you have measurement protocols of measurement protocols on a system, you can simulate them by flattening them to just single measurement protocols, and similar intuitions for these other things. So you can then make the idea I had in pictures. And now it turns out, because this thing is comonoidal and because these non-contextual models are closed under the tensor product, you can then make a precise definition like this. And I think I'm running short in time, so I'll just show one slide which gives the main results. So now the big picture thing you get out of this is that, first of all, this contextual fraction, which is a measure of contextuality, is actually a monotone for this setup. And there's a whole hierarchy of already known notions of being contextual in different strengths, and they can all be given categorical interpretations in terms of having a simulation from a trivial model in a suitable category. So this one is exactly in the category I just defined, but you could relax it a bit by saying, oh yeah, maybe you want the push forward to be equal only after if you just remember whether outcome was possible or not. And moreover, the thing is, you get the same notion if you look at things in terms of the free operations instead. And finally, there's an interesting no cloning result or something of that flavor, which roughly says that, oh, if you had a single system, when can you use it to simulate two copies of itself? Well, that turns out to be possible only if the system was free to begin with. So in particular, if someone gives us a PR box, then we have to be very careful with how we use it, because we can't use it to get more copies of the same thing. I think I'll end there. Thanks.
Okay, questions? Yes?
Can you also define non-contextual in terms of the measurement protocol Comonadic?
So that something is non-contextual. What kind of thing do you have in mind?
I don't know. I don't know what the co-algebra is for this.
Sure. Yeah. So I think that we haven't. It's surprisingly complicated to work with. So we haven't worked out yet what the co-algebras are. But we do have a hunch. But I think that sort of relates to something slightly different, and I'm not going to go there now.
Thank you again.